Okay, so next speaker is Kevin Luhman. We have invited to talk this time. So to go to the session and ask questions, you need to get out of Ruben's session and go to the Kevin Luhman's session now, as I did. Okay. So Kevin, you have 20 minutes for your talk. And Kevin is associate professor at the University of Chicago, and he'll be talking about the brown dwarf. So we are a little bit early, so let's maybe like wait for 1 more minute. Yeah, so people can join on time. Some people probably like plan to join on like 6:20 in Chilean time, or yeah. So while we are waiting for like a couple of minutes, I'm gonna go back to the other session if there was any questions. Okay, I didn't miss any questions. All right. Oh, I mispronounced your affiliation. So Kevin is a professor at Pennsylvania State University. I apologize for that. Mm-hmm. All right, we are like 1 minute ahead, but I think we can start. So why don't you go ahead?
Okay, thanks. Okay, so today I'd like to discuss some of the work that I've done searching for low mass brown dwarfs in nearby star forming regions. So here's a schematic of the IMF as of 1995. So this shows mass in units of solar masses at the bottom and Jupiter masses along the top. And then, as all of you know, in 1995, the first brown dwarfs were discovered, and that enabled brown dwarfs to be found in large enough numbers eventually for their mass function to begin to be measured. And a major goal of my work for many years has been to identify the minimum mass of the IMF. In other words, what is the smallest mass at which brown dwarfs exist, the smallest mass at which the star formation process operates. And to illustrate how one might go about searching for brown dwarfs at very small masses, I began with an HR diagram, and I'm going to zoom into the lower right-hand corner at low luminosities and cold temperatures. So here's 4,000 Kelvin on the left, less than 100 Kelvin on the right, and then luminosity. And here are the temperature ranges for M, L, T, and Y types. And these dots are the predicted luminosities and temperatures for a low mass star, a high mass brown dwarf, and a Jupiter mass brown dwarf, all in the age of 1 million years, so soon after birth. And this shows the predicted evolution over time to eventually 10 billion years. And so the low mass star eventually starts fusing hydrogen, stabilizes its luminosity and temperature, whereas the brown dwarfs, of course, never fuse hydrogen stably and get cooler and fainter forever. And so the point of this diagram is that if you want to find brown dwarfs at very, very small masses, like maybe a few Jupiter masses, if you're looking for them at those low masses when they're old, billions of years old, well, their luminosities are going to be extremely faint. And so in that case, you need to look in the solar neighborhood within about 10 or 20 or 30 parsecs. But the alternative is to look for them when they're young, because when they're young, they're still relatively luminous and warm. And the nearest young star-forming regions and open clusters are at distances of a few hundred parsecs. And so those are the two main hunting grounds for brown dwarfs, the solar neighborhood and the nearest young stellar populations. And in fact, the very first brown dwarfs found in 1995 were found in both of those environments, both as a companion to a nearby field star and as a free-floating object in the Pleiades open cluster. So here are examples of low-resolution spectra at red optical and infrared wavelengths for M, L, T, and Y types. And then we can see these strong bands due to absorption from water and methane in the case of T dwarfs. And so because of these bands, because of this complicated structure in their spectrum, these objects can produce distinctive colors in broadband filters. And so we can use just normal broadband filters to identify brown dwarfs based on their distinctive colors. But another alternative is to use custom-made filters, narrowband and medium band filters that are designed to coincide with these absorption bands and the continua next to them. And so for instance, HST and James Webb have filters of this kind, as well as a few ground-based telescopes, including CFHT. So for instance, Massimo Roberto has used HST imaging in filters of this kind to search for very low mass brown dwarfs at planetary masses in Orion. And Caitlin Allers and Mike Liu and collaborators have done the same thing with the CFHT and other star forming regions. And so here are examples of some of the nearby star forming regions that I've studied. And these are all shown at roughly the same physical scale. And so as you can see, they span a wide range of stellar densities. On the one hand, you have Taurus, which is spread across 100 square degrees. On the other extreme, you have the trapezium cluster in Orion. Now, in the case of the more compact clusters, the imaging might come from either deep imaging with ground-based telescopes or with HST. But in the case of the more broadly distributed populations in Taurus or Persco, you often have to rely on sort of medium depth, wide field imaging from sources like UKIDS or VHS or Pan-STARRS. So here we're back to the low resolution spectra that I showed you before. So the M types, so the late M types, these objects are still bright enough at optical wavelengths that they can be observed with ground-based telescopes. And so for instance, this top spectrum shown here is a Gemini GMOS spectrum of the first known L dwarf in the Taurus star forming region, which was found more than a decade ago. And so that has a mass of about 10 Jupiter masses. So again, for the M types, it's feasible to observe them with optical telescopes. But as you can see, these things are brighter, quite a bit brighter than near infrared. So if you really want to get spectra of the planetary mass brown dwarfs, very, very low masses, you're better off going to near infrared. And so for instance, here's a GNIRS spectrum of what at the time was the coolest known member of the chameleon star forming region. This spectrum, it's labeled as M9.5. Here it's compared to a previously known one, was warmer M8. So this spectrum was obtained during science verification observations at GNIRS. And actually, I think this was the first paper that presented GNIRS data. And the next year, we used GNIRS once again to get a spectrum of an even fainter and cooler member of chameleon, which is shown here in the top spectrum. So it's about L0. The middle spectrum is the one I just showed you. And then it turns out that both of those brown dwarfs and chameleon, which again are only around 10 Jupiter masses, they both show excess emission at mid-infrared wavelengths, indicating the presence of a disk. So these 3 points here are J, H, and K. And then these 4 points here are from IRAC on Spitzer. And so Spitzer observations demonstrated that those brown dwarfs and others have infrared excess emission, indicating the presence of a disk. And at that time, they were the least massive brown dwarfs known to harbor disks. And that was pretty neat because that demonstrated that free-floating brown dwarfs down to planetary masses, like 8, 10 Jupiter masses, brown dwarfs, those very small masses, had the ingredients around them for making planets. So that indicates there might be miniature solar systems out there where the central suns have masses of maybe 5 to 10 Jupiter masses. And here's an example of a recent HR diagram in the Taurus star forming region from a paper in 2019. So the black points were previously known members of Taurus. The red circles were new members that we found in the survey. And here you can see how the new members extended the sequence down to fainter magnitudes and cooler temperatures. And now see, these slides will show a summary of all the known brown dwarfs in a sample of star-forming regions and the ones found with Gemini and confirmed with Gemini spectra. So for instance, Taurus has almost 100 known brown dwarfs at this time, and about a quarter of them have been confirmed with spectroscopy with Gemini, mostly GNIRS, but a few with GMOS. And so you can see here how we rely on Gemini for getting spectra of the very faintest brown dwarfs in these regions. Here's another nearby star-forming region, Chameleon. Chameleon is not as populated as Taurus. There, it has about 39 known brown dwarfs, and 13 of which have been confirmed with Gemini. Here's IC348. So it has 71 known brown dwarfs. And you can see how most of the faintest ones have been confirmed with Gemini once again, about 24 of them. And some of these spectra were obtained both from my papers and also in this paper as well, with GNIRS. And here's Upper SCO. So Upper SCO is much richer than the previous regions. It has more than 200 known brown dwarfs, and 77 of the faintest ones have been confirmed with Gemini, both in my work and in this study here. So here's the schematic of the IMF that I showed you earlier before the discovery of brown dwarfs. And so over the last 2 decades, surveys of that kind have extended the mass function for brown dwarfs down to lower and lower masses. And so currently, we've measured the mass function down to about 5 Jupiter masses. And so far, it shows no indication of approaching or detecting a lower limit or a lower mass cutoff in the IMF. So it's still going strong. And so it remains to be seen what the minimum mass of the IMF is. We need deep observations to go down to 3, 4, 1 Jupiter mass, and hopefully eventually measure the minimum mass of the IMF. And as I mentioned, that the current measurements go down to 5 Jupiter masses, and that overlaps with the masses of giant planetary companions found from radial velocity surveys. So again, many of these least massive objects have planetary masses. And so here's a summary of this work. So in total, more than 100 brown dwarfs down to 5 Jupiter masses have been discovered and confirmed with Gemini spectra. And that work has resulted in about 15 papers since 2004. And the more recent ones have been led by a former grad student, Taryn Esplin. And there have also been a number of other astronomers who have discovered planetary-mass brown dwarfs in other circumstances in the solar neighborhood, in young nearby associations, and in other nearby young clusters. And as I mentioned, we need deeper observations to actually measure what the minimum mass of the IMF is, to go below 5 Jupiter masses. Okay, so that's all I have for today, so I'll stop there and take questions.
So thanks for the talk. So there are 2 questions. Oh, yeah, you can see that. So first question is, can data from Vera Rubin Observatory be used to identify new brown dwarfs? That's posted by CE.
Yeah, so that's a great question. So the answer is yes, definitely. So Rubin will provide very deep optical images, which are very useful for surveys of this kind. And so what you would need to do is combine Rubin optical images with comparably deep near-infrared images. And data of that kind have been obtained by various surveys like VHS and other surveys on VISTA. So definitely you can combine Rubin with other near-infrared imaging surveys to identify brown dwarfs of this kind. And that's the next step in this work.
Yeah, thanks for that answer. Second question is, how was the free-floating brown dwarf detected? Was it serendipity?
Oh, do you mean the very first one in the Pleiades? I'm guessing that was the question that was the one was referred to. So yeah, I mentioned that one of the very first brown dwarfs discovered, found in 1995, was found as a member of the Pleiades open cluster. And that was found through a survey that was meant to, it was a survey searching for low mass brown dwarfs and or low mass stars and brown dwarfs. And so they did mean to find objects of that kind in the Pleiades. It wasn't an accident.
Okay, so next question is, what is known about the multiplicity of brown dwarfs?
Well, the multiplicity of brown dwarfs is lower than that of like low mass stars and solar mass stars. Basically, the multiplicity fraction is higher for higher primary masses, and it decreases steadily down to low mass stars and brown dwarfs. And so the binary fraction for brown dwarfs is probably around 20%, something like that.
Next question I see is, Gemini has obviously been important to this work up to the present. Looking to the future, what resources will be the key for your research project?
Right. So, I mentioned earlier how there are some of these regions, these star-forming regions, that are very large on the sky, and there are others that are much more compact. For the ones that are very compact, the best approach is to use James Webb to perform very, very deep imaging to look for brown dwarfs down to a Jupiter mass. So James Webb should be able to detect free-floating brown dwarfs down to the mass of Jupiter in places like Orion. And in fact, there are guaranteed time observations with James Webb that are planned for Orion, IC348, NGC 1333, NGC 2024. And so it's likely that James Webb will find brown dwarfs, if they exist, down to those masses in a few years. And so that's for the very compact clusters. For the very large regions on the sky, a good approach is to use the Roman telescope. So the Roman telescope will provide very low resolution near-infrared spectra, and that's perfect for finding brown dwarfs of this kind. So you can use Rubin and Roman for the very big regions and James Webb for the compact regions.
So James Webb, you'll be using mainly the imaging instrument or like spectroscopy?
Well, so you would initially obtain imaging and filters that are designed to measure the steam and methane bands. And then you identify the candidate brown dwarfs based on the imaging and then get spectra of them. So first imaging and then spectra.
Right. And what about other like future ELT facilities planned?
Yeah, so you could do much of the same.
Telescopes.
Yeah, I mean, so the big ground-based telescopes, you could definitely do the same sort of work that I mentioned with James Webb. You could do with the ground-based telescopes as well, ELT.
And what other like Gemini instruments, or future instrument and current instrument you'll be using?
Well, for this kind of work, the best Gemini instrument is GNIRS, because you need to get spectra of these things, and the best configuration for a spectrograph is one that covers the entire near-infrared at low resolution and high sensitivity. And so that's a very well-suited instrument, GNIRS, for work of this kind.
So we have a future high-resolution near-infrared spectrograph, as you well know, IGRINS and IGRINS. Mm-hmm. Well, IGRINS is being currently used. So, yeah, what kind of improvement in your science you can do with IGRINS and IGRINS2?
Yeah, well, at a very high resolution, IGRINS can be used to observe the somewhat more massive and brighter brown dwarfs. And there you can do all kinds of other sophisticated analysis. You can look for planets from radial velocity surveys and various other studies of their atmospheres. So there's definitely a lot of work you can do with IGRINS for the slightly more massive and brighter brown dwarfs.
Thank you for that answer. There's another question posted by Tom Jibat. For the brown dwarfs with the masses of 5 to 10 Jupiter mass, what fraction of them is known to have disks? And what are the masses of the disk? And the third question of this one is, what masses and the type of planets might form around them?
So up until this point, the most sensitive telescope we've had for detecting disks around brown dwarfs has been Spitzer. And Spitzer was capable of detecting the mid-infrared excesses from disks for brown dwarfs down to about 10 Jupiter masses, maybe 8 Jupiter masses. But if you go below that mass, the Spitzer photometry isn't, it's just too noisy at that point. And so for instance, for the ones we found that are like 5, 6, 7 Jupiter masses, there the Spitzer photometry is quite uncertain. And so it's unclear whether they have disks or not. And so, but you know, like down to 10 Jupiter masses, the disk fraction for brown dwarfs is basically the same as that for low mass stars. You know, it depends on age. So for younger ages, it's higher. For older ages, it's lower. But the disk fraction for brown dwarfs and stars, low mass stars, are about the same, down to 10 Jupiter masses. Now, below 10 Jupiter masses, we don't really know what the disk fraction is. And for that, we're going to have to rely on either ALMA or James Webb. And there was a question about the masses of those disks. So millimeter observations indicate that the masses, basically the ratio of the disk mass to the brown dwarf mass, it seems to be roughly the same as for stars. It's, you know, maybe 1% or 0.5% or something like that. And so that means that if you have a 10 Jupiter mass brown dwarf, its disk probably has a mass of 1/10 of Jupiter mass or something like that. So it's unlikely that the disks would have enough mass to make gas giants, but you could definitely form rocky planets around these low mass brown dwarfs. So if these planetary mass brown dwarfs have planets around them, they're almost certainly rocky rather than being gas giants.
Okay, thanks for answering the question. All right, so I see the question posted by Guillermo Blanc. In the mass overlap region, how do you observationally distinguish planets from brown dwarf?
Well, that's a great question. So there's actually
Yeah.
another slide coming up that addresses that. So so some of you may know there are two main options for dividing a line between brown dwarfs and planets. One would be based on mass, where you might say that if a body is below the deuterium burning limit, which is 13 Jupiter masses, you might call it a planet. And if it's higher than that mass, it's a brown dwarf. But instead, I prefer a definition based on how they form. So I would say that a substellar body that forms within a disk around another more massive body, that's a planet. Whereas a substellar body that forms from a collapsing cloud core, like a star, I would say that's a brown dwarf, no matter how small in mass it is. So if it forms like a star, I would say it's a brown dwarf. Now, as far as how you distinguish between the two, how you can tell how it formed, well, that's often kind of tricky. Now, the nice thing about the star-forming regions is that these regions are only a few million years old. So it seems unlikely there's been enough time for planets to form around stars and then get ejected for us to see them free-floating. So if you see a free-floating body in a star-forming region, it's probably formed like a star. It's probably a brown dwarf. And one piece of evidence for that is that many of these brown dwarfs have their own disks around them. And so that suggests they weren't ejected. You know, if you have a brown dwarf that has a disk that's 10 AU in size or something, it probably wasn't ejected and carried that disk with it out of another planetary system. So because of the youth of these regions, it's likely that most of the brown dwarfs I've talked about probably form like stars.
Okay, so let's move on to next question. So Su asked, will it be possible to resolve these brown dwarf disks with GNIRS IFU?
Probably not. They're probably too small. I mean, one problem is that it appears that brown dwarfs, that as you go to smaller and smaller masses from stars to brown dwarfs, the disk masses become smaller and their diameters become smaller too. And so So at these wavelengths, like optical infrared wavelengths, you probably wouldn't be able to, I mean, you're talking about sizes of like 1/10 of an arc second. I mean, there might be special circumstances where if you have a disk that's edge on or some favorable geometry that gives you a good contrast of the disk compared to the brown dwarf, you might be able to resolve something. But instead, probably your best bet is using ALMA for that.
Okay, so I'm gonna refresh again. I think we covered most of the questions. And thanks for making your talk short, so we had like plenty of
Right.
time for this
Yeah, I
discussion.
kinda
It
raced
was
right through
great,
it.
I think. All right. Yeah, I don't see any other additional questions. So let's thank our speakers.